So today I thought I would just make a video going over some research I've been doing for the last, I don't know, 6 years now, off and on, about a conjecture. It's called the Goldbach Conjecture. And it's a very simple conjecture to state. It says that if you give me any even number that is greater than 2, that number can be written as the sum of 2 prime numbers. And that's all. The conjecture's been around since 1742. No one's been able to prove it or find a counterexample. And so that gives you an idea of how difficult it's been to try and find a proof for this. And that statements that can be said in a very simple way oftentimes are the most difficult to prove. And so the idea behind this, I want to show you what mathematics research looks like. Because I think a lot of people, when they think about mathematicians or they think about math research in general, they're really just thinking we play around with numbers all day, and that's not the case. We are usually looking for general relationships, and there's an art to it, there is a beauty to it. And most people just don't get to really see what goes into it. So this video is really about how research is done on these problems. And so I felt like the easiest way to make this video was to cover just one portion of the paper that I've been working on. And I'll have a link to that paper in the description and probably in the comments. But there's really 3 proofs in the paper, and we're just going to cover the Goldbach proof. But it turns out that if you can prove that every even number is the sum of 2 primes, then with this same method, you can prove every number is the difference of 2 primes as well. And so the way I've constructed this video, or the way at least I plan on doing this, is on this side of the board, I'm going to have kind of the general statements of the paper written out, and I'll go over some of the notation here for those of you who don't know what this notation is. But this is really just kind of a synopsis of the portion of the paper that I'm going to go over. And then on this side of the board, those statements that need to be proven directly, I will go over that proof formally on this section of the board. And so the first thing I want to cover is, how do you come up with a proof of this problem? And again, it's been around since 1742. And what I tried to do was to come up with a counterexample, or at least come up with the necessary and sufficient conditions required for a counterexample. And so what I did was I simply asked, what would it mean for there to exist a counterexample to this, and can we find some sort of consequences from that? So as an example, and this is in the paper in the introduction, but as an example, let's say that we wanted to prove that 20 was the sum of 2 prime numbers, right? And so one thing we can do with that is say, okay, well, if you give me all the primes up to half of that number, so up to 10, and those primes are given by the set 2, 3, 5, and 7, then I know 20 can be written as sum Q1 plus 2. It can also be written as sum Q2 plus 3, because this is the second prime. That can be written as sum Q3 plus 5, and then that can be written as sum Q4 plus 7, right? Now, of course, a simple way to do this is just to analyze and figure out what these Q's are, which we can do fairly simply. But we want to kind of get an idea of what this method is that we're looking at. And so the idea here is that if it were the case that none of these Q's were primes themselves, then we know from the fundamental theorem of arithmetic that the product of each one of these Q's has to be equal to the product of each one of these primes raised to some power. Now, of course, this power could be equal to 0, or any number of these powers could be equal to 0, right? But we should have a set of equations that looks like this, right? So if none of these are new primes, then they're each divisible by these primes up here. And if we can find integers, alpha 1, alpha 2, alpha 3, alpha 4, that satisfy this equation, then we know that 20 cannot be written as the sum of two primes. But of course, this is nonsense, right? Because when we go ahead and plug in these values, so Q1 is 18. So that's 18 times 17 times 15 times 13. And we can see that there are no sequence of alphas, which are assumed to be integers, that satisfy this equation. And so because of that, we know that at least one of these numbers over here has to be a new prime. Now notice that it doesn't tell us which one it is, right? Or how many there are, but that doesn't matter. We know that because this equation cannot be satisfied with integers, alpha, 1, 2, 3, and 4, then one of these has to be a new prime, which means 20 is written as the sum of two primes. And that's really been the difficulty in trying to find a proof for this conjecture, is the fact that we don't know how many primes there are in a given range. And we really don't know when a number is prime to begin with. It's hard to determine if a number is prime once you get up to really large numbers. And so we can generalize this. And that's what this paper is going to do, is we're going to show that if there exists a counterexample to the Goldbach conjecture, then that means we can write 2a is equal to qi plus pi, right? These i's are just indexes. These are all assumed to be primes, so all these primes are up to a in this case. And then q is just an integer. But again, if none of these are primes, well, all of these are primes, and so that means the product, and so the way we write product here is I equals 1 up to pi of a, which is the number of primes up to a. And then that has to be equal to the product of all the primes, and then there's some unique alpha I for each prime that satisfies this condition. And so the nice thing about this is we can just do substitution, and so we get this really, I think, beautiful equation that would give us a counterexample to the Goldbach conjecture, as long as 2a is a solution to this. Now there are numbers that do satisfy this criteria. And so 6 is an example of that. So if we look at 6, 6 can be written as 2 squared plus 2, which is also 3 plus 3. And notice here that if I take each one of these q's, right, then 2 squared times 3 is obviously equal to 2 to some power times 3 to some power, where these are integers, right? But notice that 6 is divisible by both 2 and 3. And what we're going to find at the end of this paper, and the reason why we're going to be able to prove this conjecture, is that these are the form for any 2a that satisfies this condition. That is, 2a must be equal to pi to the alpha I plus pi for all primes up to a. And the reason this is important is because, well, this means that twice a has to be divisible by each prime up to up to A because, well, pi is clearly less than 2a, which means this power here must always be greater than 0, right? And so this requires all of the primes up to a to be divisors of 2a, but we know from another theorem called Chebyshev's theorem that there's always a prime between a and twice a, which means that 2a would have to be greater than or equal to a primorial. But this can't hold. In fact, you can see that once we get up to a is equal to 5, this doesn't hold, right? Because 5 primorial is equal to 2 times 3 times 5, which is equal to 30. But then 2 times 5 is equal to 10. And that pattern is just going to keep growing because there's always going to be a prime between then 5 and 10, which means this is going to get multiplied and become even greater. And so this is really the idea behind the proof of this conjecture, is to find the form of a counterexample that would exist if the Goldbach conjecture were false, and then to show that, in fact, there are no counterexamples. And of course, if there are no counterexamples to a conjecture, then the conjecture must be true. And so let's go ahead and start with the paper. And I am starting here on section 1.3, so preliminaries and definitions. And so a lot of these are just used as a way to make things easier to read and communicate. So this kind of double P here, this just represents the set of prime numbers, so 2, 3, 5, 7, 11, on to infinity. Definitions 1.4 and 1.5, so D is the set of primes that divide 2a. So for instance, if 2a was equal to 10, then the set D would consist of 2 and 5, right? If 2a was 12, then the set would consist of 2 and 3. So we're not worried about the powers, we're just worried about the actual prime divisors. And then this other P, the non-double P, is just the set of all primes less than or equal to A. Okay? And so what we're doing here, the strategy for the proof, is to assume a counterexample exists, and then show that that derives a contradiction, to show that it is impossible for a counterexample to exist. And so definition 1.8, we define what's called the Goldbach polynomial. And I think it's Goldbach polynomial type 1. And so remember, we're only dealing with the Goldbach conjecture in this video. We're not dealing with the difference of primes. So that's why you have those two different functions there. And so what this definition says is we have some polynomial. This is just saying it's a mapping from the complex to the complex. So I put a complex number in, I get a complex number out. And the way we're defining this is that for all primes in the set P, so we're picking some A, some value of A, and then for all the primes up to that A, we're assigning a unique alpha I, which is a natural number, positive number, which can be equal to 0. And the polynomial is just defined as g of z is equal to the product of z minus pi over all those primes, and then minus the product of all those primes, and then raised to some power. So each prime is raised to a different power. And then we're putting the condition on here that 2a is a root of that polynomial. And so g minus of 2a is equal to 0. Okay, so the reasoning behind this is if GA is equal to 0, then just like in the counterexample we went over, there should exist some unique alpha 1, alpha 2, alpha 3, where 2a minus pi, all those primes we're taking the product of, is equal then to some unique prime factorization here of only those primes. Next step here is to define the actual roots of the polynomial. So the fundamental theorem of algebra says that given this polynomial, if there are roots, then they're unique to that polynomial, right? And so we can factor over those roots, and that's exactly what's happening here. So g of z is equal to z minus r of k. We're taking the product over all of those roots. Now remember, repetition is allowed. I could have something like x minus 1 squared, and so that's where the sigma k comes in. Just tells us that we could have repeated roots. And of course, because these two polynomials are the same, we can set them equal, and so the product over z minus all the roots raised to their corresponding powers is equal to just the product of z minus all those primes minus this constant term, this unique factorization constant. Definition 1.1, we look at the derivative here. And the derivative of this is going to be important because if you notice, because of the chain rule, and this is going to be important for the paper, I can show that there are certain properties this derivative is going to have. And that's going to deal with whether or not we have repeated roots. Specifically repeated roots in a certain modulo prime. And so for modulo prime, we're really just taking all the numbers up to that. So we're kind of redefining the number system instead of going out to infinity. If I'm dealing with modulo, let's say 5, then I really only need to work with numbers 0 through 4, right? Because anything I have, any number I have, if I look at 11 as an example, that's what we say is congruent to 1 mod 5, because I can write that as 2 times 5 plus 1, right? I can write it as some number times 5 with a remainder of 1. And so we'll get into that a little bit more. And theorem 1.11 is really where we start getting into the proof of this. And so what this theorem says is that the Goldbach conjecture is false. This upside down t, just a shorthand way to write false. Goldbach conjecture is false if and only if there exists some polynomial where 2a is equal to 0 and a is greater than 3. And so let's just go ahead and prove this really quick. So remember we said that we're going to assume a counterexample exists, 2a. And so that means 2a is equal to qi plus pi, right? And this is ranging over all the primes such that pi is less than or equal to a, right? So q1 plus 2, q2 plus 3, all the way down, right? But if 2a is a counterexample, well, since I know that these are all primes, again, none of these can be primes. And so what we're left with then is some unique factorization. So the product over all of these q's must be equal to some unique prime factorization of only the primes pi, right? But of course, now I can go ahead and substitute in each q, which we showed earlier. And so these two things, well, each qi is equal to 2a minus pi. And so now I'm multiplying over the same range, 2a minus pi is equal to this, right? But notice that this is the exact form of the Goldbach polynomial, right? Because if I subtract this from the side, I get 0, which is exactly what happens over here. So therefore, we can conclude that 2a must be a root of this polynomial, right? Or that there exists some Goldbach polynomial. All right, but it's an if and only if, so we need to go the other way. So the first direction, we assumed the counterexample exists. The second direction, let's go ahead and assume, I'll erase this. So remember, if a counterexample exists, then g of 2a is equal to 0 for that polynomial. But now let's assume that g of 2a is equal to 0. Well, what does that mean? That means that there exists some prime factorization where 2a minus pi is equal to this product. That should be 1 pi to the alpha I. Right? So that has to hold, because if this is equal to 0, then I can just move this over. But notice that 2a minus pi must be an integer, and it must be unique. Right? And since since this is an integer, well, it has to be divisible by only the primes less than a, which means I can write 2a as equal to qi plus pi. But I know that none of these qi's are new primes, that they have to be divisible by only the primes up to a, because that relationship is held. So if that's the case, this must be a counterexample. It cannot be written as the sum of two prime numbers. And so we've now proven this if and only if condition. Right? Of course, we're assuming in each case that 2a is greater than 3, but that's how we would go about doing this. And so it turns out that when you look at those two sets of equations, it's not so easy. At least it's not to me, to find out what 2a looks like, right? And so it's one of those things that you learn early on in math, that you may look at a special case of something and then find that it's actually really hard to prove that special case. But if I generalize, so right here I've generalized to a polynomial, which you would think would be harder to prove. But it turns out when we go to this polynomial representation, now I can use other tools at my disposal, like calculus and things like Hensel's lemma. And so what Hensel's lemma says, and this is really important, this is used for lifting roots. So what Hensel's lemma says is, given a function, a polynomial over the integers, then if we have a root of that polynomial in some mod prime, right? So f of r is congruent to 0 mod prime. Doesn't mean it's equal, right? But it means congruent to 0 mod prime, and the derivative is not congruent to 0. Then we can essentially lift this root to higher order terms, right? And you may look at this and say, okay, well, why does this have any value at all? And the reason is because we know 2a is a root. And we can begin saying, okay, well, if I know 2a is congruent, so the primes that divide 2a, I know 2a is going to be congruent to 0 in that mod. And so now I can have a way of generating the form of 2a in terms of these roots and Hensel lifting. And so I'm going to give you kind of an idea of what that looks like. So in this next section, I want to go over sort of the strategy here. And then we'll move from there. So when we are talking about p-adic analysis, which is really just the prime numbers, or an analysis of writing numbers as series of primes. That's really how we're going to look at it for this, this talk. if we look at 10 as an example, there's only one way to write 10 in a series mod 3, and that is 1 plus 3 squared. Okay? There's no other way to write this. We can also look at it in terms of, so this would be a three-adic representation of 10. And what this says is that if you give me a number, I can always write that in terms of some t naught plus p times t1 plus p squared times t2, on and on and on. And since this is an integer, there should be some finite representation of this. But the caveat is that all of these t's are in what's called the field of mod p, which just means t is in the set of 0, 1, all the way up to p minus 1. Right? So these are the only numbers we can use for these t's. And so notice what happens here. With 10, we certainly have 1, which is in the three-adic field here, 0, 1, or 2. And so 1 plus 1 times 3 squared. It's the only way this can be written. If we look at 10 in 7 adics, right? So we're dealing with the numbers 0, 1, up to 6. And so 10 is 3 plus 1 times 7 in this case, right? That's not 17, it's 1 times 7. So notice our T0 is 3, and then this last one here is just 1. And so we can get this series. This series is unique. And so the idea now is to say, okay, well, I know that my counterexample 2a is equal to qi plus pi for all of the primes up to a. There's some qi. For each prime up to a, there's some unique qi satisfying that condition. But I also know from p-adic analysis that there is some unique series of t's that will terminate at some point pi n tn. Right? And now the question is, okay, well, maybe I can find these t's here. And in fact, I can because of Hensel's lemma. Hensel's lemma allows me to keep lifting. And since I know 2a is already a root of this polynomial, it has to be a root in mod p. And so now I can begin to ask, okay, well, what is the form of primes that satisfy these two equations, right? Because I'm really interested in this form here is equal to this. All right, so I'm really interested in these divisibility properties. All right, that's ultimately what I'm interested in. And so let's try and analyze what some of these divisibility properties look like. And then once we have that, we get closer and closer to constructing 2a. The strategy here is to see if there's a relationship between these alpha i's and these t's in some way. And we will see that there is, and there's a very important relationship. And so let's go ahead and look at the divisibility properties. So this is section 2.2, and we're looking at a proof of lemmas 2.2 and 2.4. And so we're really going up to proposition 2.6 here. But I just want to go through these quickly. So lemma 2.2 says for any alpha I, it follows that alpha I is greater than 0 if and only if pi divides. So alpha I is greater than 0 if and only if pi divides qi or pi divides some qj that's not equal to I. This is lemma 2.2, I think, right? Okay, and so this is pretty easy to see. Remember, we have the sets of equations Q1 plus PI and the product of all these Q's must be equal to some unique prime factorization over only the primes up to A, right? And so notice what happens. If alpha I is greater than 1, in this case, then obviously that prime has to divide either its corresponding QI or it has to divide some other QJ, right? Because these are integers, so that has to be the case. Going the other direction, so if PI divides its corresponding QI or any other QJ, well, then PI is a divisor of this side. But that means it has to be a divisor of this side, which means PI, since those are primes, divides PI to the alpha I, and this means, of course, alpha I must be greater, it should be greater than or equal to 1. Greater than or equal to 1, right? So that's sufficient to prove lemma 2.2. We can go lemma 2.3. Again, we're using these same equations, and lemma 2.3 says that PI is a divisor of QI if and only if PI is a divisor of 2A, right? Yeah. And this just follows trivially. If PI divides QI, it's a divisor of this side, which means it has to divide 2A. Conversely, if PI divides 2A, well, it has to be a divisor of this side, so it has to divide QI. And so that's fairly simple. Lemma 2.4 is actually the most important one in the paper, or at least one of the most important ones in the paper. And that says that if PI divides QI, then it does not divide any other QJ. And you'll see why this is important here as we move forward. But again, looking at 2A is equal to QI plus PI, this holds for all PI, right? For every PI, there's going to exist some unique QI. And so we can just say QI plus PI is equal to QJ plus PJ, right? And notice that if PI is a divisor of QI and PI divides QJ, well, what do we get? PI divides this and PI divides this. Then PI has to divide PJ. But of course, these are both primes. And so it follows that PI does not divide PJ. Therefore, we can conclude that if PI is a divisor of QI, then PI cannot divide any other QJ, because we would lead to this contradiction. Okay? And so these are really important in helping us construct the Qs and ultimately the form of 2A. And so this is going to be the last thing that we mention here. So I'm going to get rid of these, and we're going to go over the last two propositions of that section. And so, let's see. So we have these two sets of equations, and then proposition 2.5 just says, so prop 2.5 just says that if PI divides 2A, then 2A has to be of the form Ni times PI to the alpha I plus PI, such that n is not equal to 0 and the greatest common divisor of ni and pi is equal to 1. Okay? And so let's just kind of think through logically why this makes sense. Well, so we already showed that if pi was a divisor of 2a, right, then it had to be a divisor of qi, right? And that holds from limits 2.2 and 2.4. And so pi divides 2a, it has to divide qi, which means it doesn't divide any other qj. Well, the maximum power it can be here is alpha I, right? And so then 2a must be equal to some number that's non-zero times pi to the alpha I, and then just plus pi, right? So qi is equal, has to be equal to this, right? Again, it's because of this unique prime factorization of the fact that if pi divides its corresponding qi, it can't divide any other qj, and so qi just has to be equal to pi to the alpha I. If, on the other hand, so looking at proposition 2.6, so prop 2.6 says that if alpha I is greater than 0 and p, did I say alpha I in this case? Yeah, I did. And pi doesn't divide 2a, then 2a must be equal to, I think I use n, as I use m. So m I times pi to the omega I plus pi such that omega I is less than or equal to alpha I, right? So I think that's, or plus pj. Yeah. All right. So this is a j. That's an I. And that's going to be an mj. Okay. So a little bit of details here. And mj not equal to 0, and the GCD of mj and pi is equal to 1. All right, so a lot of conditions here, but you'll see it's pretty obvious. So given that alpha I is greater than 0 and pi doesn't divide 2a, that means pi doesn't divide its corresponding qi, which means from limits 2.2 through 2.4 that pi has to divide some other qj, right? And so this is why that pj comes in, because 2a is also equal to qj plus pj, where this pj is a prime up to a. Now, the issue that we run into is we don't know if it divides only that qj. It could also divide another q, right? And so that's why we have this condition that this omega I has to be less than or equal to alpha I. It obviously can't be greater because that's the maximum value we can have, but it's not necessarily equal either, because it could be the case that other q's are divisible by that same prime because it doesn't divide 2a. And then the greatest common divisor is just put on here because, well, this is the maximum power. If this was divisible by pi, then it would just get absorbed and I would have omega I plus 1. Well, I can just rescale that as omega I, right? So that's where this greatest common divisor comes in. And it obviously can't be equal to 0 because 2a is greater than pj, right? So that's a proof of those lemmas and propositions. And so notice we now have an idea of what the form of 2a should look like, right? The question is, how do we hone in on that even more? And there's really not enough information in those two sets of equations, right? So this is where we need to move to Hensel's lemma. and finding out how to construct 2A, kind of a brute force method. And so in section 2.3, we derive the Hensel-Goldbach equations. And the Hensel's lemma here, again, is defined as these two conditions, that the root is congruent to 0 mod p, but the derivative evaluated at that root is not congruent to 0 mod p. That eliminates the possibility of multiple roots, and so you know it has to be a unique expansion. And so we want to show that this in fact can be used. And so for proposition 2.7, so proposition 2.7 says that there exists a unique root in these Goldbach roots here. So it's an actual root of the polynomial such that Ri is congruent to 0 mod pi. And when we evaluate the derivative, this is not congruent to 0 mod pi. Okay? So this is telling us we can use Hensel's lemma, and we can prove that directly. And so the first thing to note here is that if I evaluate, and this is if and only if alpha I is greater than 0. Right? And so let's just evaluate this directly. So if I look at g of 0, right? So what's this going to be? Well, it's just going to be equal to -1 to the pi of a, so that's how many primes I have, and then just times a primorial, which by definition is the product of all primes up to a. And then I have this other term here, minus all the primes in the prime set. So these are all the primes up to a. And then I have this unique factorization. So this is just my function evaluated at 0, my polynomial evaluated at 0 in this case. And let's look at the derivative as well. All right, so the derivative in this case evaluated at 0. Well, notice we can use the definition of the derivative, and what we're left with again is going to be -1 to the pi of a times a primorial over 1, and this is going to be minus p1 minus 1 over p2 all the way up to minus 1 over p pi of a. Right? Now I could go ahead and divide through by a -1, and this is pi of a to the -1, and then I just have the primorial of 1 over p1 plus p2 all the way up to this. Okay? So the reason this is important is let's not assume. This is congruent to 0 mod pi if and only if alpha I is greater than 0, right? Because the primorial is clearly congruent to 0 for any mod pi I pick, because these pi's are in the prime set of A. So they're going to be contained in here. So this is 0. So the only way this is 0 is if that corresponding alpha I is equal to 0, or is greater than 0, right? That's the only way. So it's an if and only if. But now let's look at the derivative evaluated at 0 in this case. If we look at this derivative evaluated at 0, then whatever pi I pick from, notice that a primorial divided by 2 is just the product of all the odd primes, but then every other term here is divisible by 2. And so if I pick mod 2, then the only one that disappears, or the only one that stays, is this one here, right? Because all of these are divisible by P1. If I pick P2, then this one stays, because it's the only one now not divisible by P2, but everything else is divisible by P2. And so we know that this here is congruent to negative pi of a minus 1 times a primorial over pi, mod pi, which by definition is not 0, mod pi. We don't know what it is, we don't care, we know it's not 0. So this function here, 0 is a root if and only if alpha I is greater than 0. And the derivative of that evaluated at that root is non-zero, which means we can use Hensel's lemma. And that also means that there is a unique Ri. So there's a unique root in here that we can use Hensel's lemma to construct. And that's where this lifting of the polynomial comes from. So I can get my T0, which I know is 0 in this case. Then I can figure out what T1 is, times P. Then I can figure out what T2 is, and I can keep lifting until, in the case of 2a, I get zeros from then on out. And that's because 2a is finite, so I'm only going to have a finite number of lifts. So that's really what we're looking at here. So we can use Hensel's lemma for this. So proposition 2.7 is proven pretty easily. Definition 2.8, we call this root, so there's a reason why I chose I here to match up with this I. So we're calling this the principal root of that function. So definition 2.8 is the principal root of pi. And so whenever we see a principal root, we know that that alpha I is greater than 0. So as an example, 2 is always going to be a principal root, right? Because 2a, so 2a is even, and then q1 plus 2, well, whatever q is, it has to be divisible by 2, right? And so 2 is going to have a principal root. So now we can begin to build up 2a in terms of these two-adic expansions. So that allows us to use Hensel's lemma. We can also see that 2a is not a repeated root. So in corollary 2.9, 2a is not a repeated root. So let's just go ahead and prove that real quick. Yeah. All right. So the reason it's not a repeated root is because this derivative here, when we evaluate this derivative, it's important to recognize that there's no prime that divides this derivative, right? There's absolutely no prime that divides that. Well, because 2a obviously has to be constructed of only the primes up to a, and there's no prime in this divisor set that divides this derivative, then the GCD of 2a and the derivative evaluated at 0 must be equal to 1. Well, if that's the case, then 2a obviously can't divide this derivative, so it can't be a repeated root. So it's fairly easy to show that's the case here. If I say things like it's not divisible by a prime, I mean in this set. It's obviously going to be divisible by a prime, but I really mean in this prime set of A. So in corollary 2.9, I go through a little bit more formal of a proof of why that's the case, but I'm not too interested in that right now. Definition 2.10 is where we really start constructing the Hensel-Goldbach equations, right? So the way we're doing this is we are using proposition 2.7 along with the definition of principal root and asking if we can construct that. So we can look at the Hensel-Goldbach equations as negative t alpha I minus mu times the derivative evaluated at our principal root. And this has to be equal to the function evaluated at that principal root mod pi alpha I minus mu plus 1, right? Such that mu is less than, such that mu is, how did I define that? Yeah, it's between alpha I and 1. Okay? So notice when it's equal to alpha I, we just get mod pi. And then we can lift all the way up to that power. Now in principle, we can lift higher than that, but we don't really know, and we don't really care to. You'll see why that's the case. And the nice thing about this, these Hensel-Goldbach equations, is that because of the definition of our function here, notice that every lift, that when we have g of Ri, right, this is just equal to the product of, I'm going to say pk in the primes times Ri minus pk, right, minus pk in the primes, pk to the alpha k. And then notice that for any mod pi to the alpha I minus mu plus 1, where this is less than alpha k, or less than alpha I, because that's contained in here, this just goes to 0. So for all alpha I between 1 and alpha I, this term just goes to 0, right? Because I'm left with mod pi to the alpha I. Well, pi to the alpha I is in here, so this just goes to 0. And so I'm left with this very nice structure. And then when alpha I is equal to 0, then we can continue lifting. But you'll see here that that's really not an issue. And so this allows for Ri, our principal root, to be constructed. Well, because it's a principal root, we know that T naught is 0, right? Because that was the whole point of evaluating the function at 0 and the derivative at 0. And so we really know it's 0 plus T1 times pi plus T2 times pi squared all the way up to T alpha I, pi to the alpha I. And then it may continue, we don't know. But remember, all of these T's are contained in the field of pi, right? So this is just going to be 0, 1, all the way up to pi minus 1. All right, so we can build up these roots, and we know that whenever alpha I is greater than 0, there's going to be some principal root. There's going to be some unique root. So now we know that there's some relationship between the alpha i's and the roots of these polynomials. And so the question now is, what is the form of this. And we're going to see that this actually gets condensed down, that all of these are going to be 0 up until we get to this ti to the alpha I. So let's go ahead and prove that. So the way we do this is, so for theorem, so let's see, theorem 2.2, or 2.12, right? Yeah, 2.12. What this is saying here is for any alpha I greater than 0, there exists a unique Ri that's a root that can be written as Ri is congruent to pi plus t alpha I, pi to the alpha I mod pi alpha I plus mu plus 1. Right? And so let's go ahead and prove this. Well, remember that we know that because Ri is a principal root, g of 0 is congruent to 0 mod pi, and g primed of 0 is not congruent to 0 mod pi. In fact, we showed that this was congruent to -1 to the pi of a minus 1 a primorial over pi mod pi. This is going to be important because it allows us to fully determine what these roots are. So using the Hensel-Goldbach equations, we know that 0 is a root, and so Ri is equal to 0 plus t1 pi plus all the way up to whatever we're dealing with. And so the way this lifting works is we then take the next lift to figure out what t1 is. So now we have t1 pi, and then this derivative is evaluated at this approximation, right, which is 0. And then this function is evaluated at that approximation. And we're doing mod pi squared in this case. Okay? So, now what I can do is I can take this pi, divide this side by pi, whatever it is, we don't really care, but let's go ahead and just do the work. So G naught, whatever that is congruent to this. Well, remember what this was, right? G0 is just equal to -1 to the pi of a times a primorial. And this is mod pi squared, right? And so now I can come along, I can go ahead and divide through by pi. If I divide this side by pi, I have to divide my, my mod by pi. And so that gives -t1 is congruent to now -1, and take this -1 divided by that, so that's pi minus 1. This becomes a primorial over pi. This becomes mod pi, okay? But remember, this is non-zero, and in fact, we know what it is already. Sorry, that should be positive t. And so we know what this derivative term is in mod p already. And so this becomes t times -1 to the pi, or to the pi of a minus 1 is congruent to, well, notice -1 to the pi of a minus 1. This is going to be a primorial over pi, a primorial over pi, mod pi. All right, this is non-zero, this is non-zero, but these are the same, which means t1 has to be congruent to 1, mod pi. Okay, so now we have the next term in this expansion. And that next term means that Ri is equal to 0 plus, well, just 1 times pi, plus all the way up. Now we go ahead and do the same thing, but remember, for every power that we're raising to, the function eliminates this term here. So now my function, g r of I, is just congruent to Ri minus pk mod pi to the alpha I minus mu plus 1, right? But Ri is just pi minus pk, right? So we're taking the product of all this, pk in p, taking the product of pk in p here, mod pi alpha I minus mu plus 1 again. But notice this is just going to be equal to 0 every single time we plug it in to these Hensel-Goldbach equations, right? Because what I have now is negative T2 pi squared, and then whatever my derivative is evaluated at pi, right, my new root, and this is congruent to g of pi mod pi cubed, right? But notice what happens in this case, right? This is always going to be 0. That's going to be 0 because I have pi minus p1 times pi minus p2 times pi. Eventually I'm going to get to pi minus pi. And that's going to give me 0, which means this side is 0. And so T2 has to be equal to 0 because this is non-zero. We already know that. And then this can't be congruent to 0 mod pi cubed. And so the only thing we're left with here is T2 must be equal to 0, T3 must be equal to 0, until we finally get to mod pi to the alpha I plus 1. And then this is going to go away. This cannot be 0 mod pi to the alpha I plus 1, just kind of by definition there in a lot of ways. And so this is non-zero, which means this side is non-zero, which means T alpha I is non-zero. And so that's just going through, the formal proof is given in theorem 2.12, where I really go over the details. But now, you know, we know what these roots are going to look like, and that this should be reminiscent of lemmas 2.2, or propositions 2.5 and 2.6, right? Because remember, 2a has to be of a similar type form whenever pi is a divisor of 2a. Right, so the final question we have, so we know what principal roots look like and what their form is. And the question is, how does this apply to 2a? As 2a is a root, and we know that 2a is a principal root in mod 2, right? But we don't necessarily know that for other alpha i's being greater than 0. But we can get around that. And so in lemma 2.3, this is 2.13, this is really where we show that there can be no form of 2a that exists as a solution to Goldbach polynomials whenever we get past a is equal to 6. And I want to introduce this by bringing in an important theorem that I mentioned in the paper, and that is the Catalan conjecture. I'm not sure if I'm saying that right, but whatever. Catalan's conjecture says that given the Diophantine equation, x to the m minus y to the n equals 1, where it's a Diophantine equation, so x, m, y, and n are all integers, that this has largest solutions 3 squared minus 2 cubed is equal to 1. And the other solutions are, of course, 3 minus 2 is equal to 1, and 2 squared minus 3 is equal to 1. That these are going to be the only solutions that are integers that exist to this equation. This is going to be very important. The strategy now, and we're just about done, the strategy now is to use everything we've had to show, along with Catalan's conjecture, you'll see where that comes in. But remember, we started with these sets of equations. 2a is equal to qi plus pi for all primes, and the product of all of these primes, so up to pi of a, of qi, is equal to some unique prime factorization of only the primes up to a, right? This is what we're concerned with solving. And we showed that it was a bit difficult. The reason we did all of this is to show that the GCD of every Q is equal to 1. And the reason this is important is because once we show this, then we will be left with equations that this has to be, each one of these Q's has to be a perfect power, right? And so let's look at what happens. We already know 2a, or 2 is a divisor of this. So assuming this is true, right, then 2 has to be equal to 2 squared, right, plus 2. And then this is equal to some other prime times alpha j plus 3. And notice what happens. We get a Catalan type equation because we're going to get 2 squared minus pj to the alpha j is equal to 1. And so that will tell us what the largest possible solution is, because we know what the largest possible solution is to this problem. And so we've done all of this to try and prove this statement here. Okay? And so let's go ahead and start this final section. You'll see where this comes into play. And so for lemma 2.13, which we're going to prove, 2.13 says alpha I is greater than 0 if and only if 2a is congruent to 0 mod pi, or 2a is congruent to some pj mod pi. And of course, this pj is assumed to be in the prime set of a, so it's a prime up to a. And so this is actually very easy to prove, right? Because remember, from previous lemmas, alpha I is greater than 0 if and only if pi is a divisor of qi, or pi is a divisor of some qj, right? And so remembering that 2a is equal to qi plus pi, which is equal to qj plus pj, for any pi and pj in the prime set of A, then what happens in this case? Well, if alpha I is greater than 0, it can only either divide its corresponding QI, right? And so in this case, QI, if PI divides QI, then 2A must be congruent to 0 mod PI, right? Alternatively, let's say alpha I is greater than 0 and PI does not divide 2A. Well, then it has to divide one of these other Q's, and so that means that 2A must be congruent to PJ mod PI. We don't know which Q it is, but we know it's not QI. And so these are the only solutions here that we have. So 2A, we know what 2A has to be congruent to. This is where these principal roots in the Hensel-Goldbach equations come in, because if we know 2A is congruent to 0 mod PI, then we know the form of 2A in terms of the principal roots here, which we kind of already knew. But the question now is, what happens if 2A is congruent to some other PJ? Is it possible for some prime PI to divide some other QJ and the product of all of these to be upheld? And that's going to be the interesting thing. So that proof of lemma 2.13 is fairly straightforward in the paper. And now what we're going to see is that turning this into a function really helped us. And so the next proposition, so prop 2.14, tells us for any PI and PJ in the prime set that the functions themselves are equal. And the proof for this is fairly trivial, right? If we look at the function here, if I plug in PI, right, eventually I'm going to hit myself, right? And eventually I'm going to hit that value because it's a product over all of those. And so that just gives us this. If, on the other hand, I pick some other PJ that's in this prime set, well, again, PJ is contained somewhere in this product, and so this is going to go to 0, and I'm left with this value. So these functions are equal at those values. And so that's going to help quite a bit in asking whether or not 2A can ever be a repeated root in some mod PI. Right, and so this is lemma 2.15, and this tells us, or gives us the consequence of this. So lemma 2.15, and this states that if PI, so if PI, if there is a prime in this prime set, and PI divides some QJ, and PI divides some QK, then the derivative of PI I cannot write. Then the derivative of PI, or PJ, I think that should be a P. PJ. It's congruent to 0 mod PI. Let's see. I just want to make sure. Yeah. Okay. So it is PJ. And so let's see why this is. So remember that we have QJ plus PJ is equal to QK plus PK. And of course, this is equal to 2A, right? And so we're assuming here that there's some prime that divides both QJ and QK, right? Which means that these are congruent to 0 mod PI. And so 2A has to be congruent to PJ, but this is then congruent to PK mod PI. Okay? Now, what we can do is look at the derivative associated with this. And if you look at the derivative evaluated at PJ, right, then notice what happens here, right? This is equal to the product of all the primes in the prime set, so Z minus PI, times 1 over Z minus P1 plus 1 over Z minus P2. And then I'm going to go over Z, PI, Z minus PJ, and then plus 1 over Z minus P pi by. Okay, so that should be enough terms there. And then what you find here is that whenever I plug in PJ, right, notice what I get here. So I'm going to have these products, PJ, hold on. What am I doing? I'm doing something wrong here. This is the problem with improv. Okay. Yeah. Okay. This should be over PK. So what's going to happen? Yeah. So what's going to happen here is when I take this derivative, and this is done in the proof here, but when I take this derivative here, everything is going to cancel except evaluating that term. So I'm left with PK in the prime set, but I'm eliminating that PJ term, right? And so then I get PJ minus PK. So I'm getting this product. So that's what happened, because I'm going to get one of these, or all of these disappearing from the product, except for one term. Kind of like what happened in the primorial, right? So that's what happened. So this gives me my product over PJ minus PK. But notice what happens here. If 2A is congruent to this, then even though this is non-zero in general, it is congruent to 0 in mod PI. And the problem with that is that it becomes a repeated root, right? And so even though it's clearly a root, so G of PJ is congruent to 0 mod PI. If 2A is congruent to PJ, because we know alpha I has to be greater than 0, because it divides these Q's, and so that follows from lemmas 2.2 and 2.4. But then, because of this congruence relationship, it's obviously a root, because looking at the Hensel-Goldbach equations, this will be 0. And then P is contained in that product, so this is going to be 0. But the problem we have is that the derivative evaluated at PJ would also be congruent to 0 mod PI. And so now what we run into is the issue that we can't use Hensel's lemma to construct this root, right? So lemma 2.5 really tells us something important, that if pi divides two q's, then the derivative is congruent to 0, which means, again, there's a non-unique way to write this as a p-adic series, right? So that becomes a bit of a problem. Now, we're going to show that that's not true in the next proposition. But the reason we prove this is because if we can show that this is not congruent to 0, then we know that there's no prime that divides any two or more q's, which means that the greatest common divisor of each q has to be 1. And because there are as many q's as there are primes, then that tells us that the greatest common divisor must be equal to 1, or that those have to be prime powers. And so that's, yeah, so in proposition 2.16, we're going to prove this. So proposition 2.16, we're going to show that the GCD of any QI and QJ is equal to 1. Okay? And so how do we do this? Well, there's a couple of ways. But remember, we showed from a previous proposition that if I evaluate, and I just want to make sure I get the notation right. So G of PI is equal to G of PJ, right? And we showed that because of how this function works. If I plug in PI in here, this term is going to go 0. I'm just off with this. If I plug in PJ, where PJ is in the prime set of A, again, this is going to go to 0 because it's a product over all those primes, and we're just left with this. So these two functions are the same, okay? And so now what we're going to do is, this means that GPI is congruent to GPJ mod pi to the k for all k greater than 0, right? So that's just going to hold for any k that we have greater than 0. And notice something here, that G evaluated at 0 must be congruent to this mod pi, right? And the question is, does this have a singular root? And it was shown that G of 0 over pi was congruent to -1 pi of a minus 1 over a primorial of pi, which is not congruent to 0 mod pi, right? And so one thing we could do is just ask, okay, well, if these two are congruent, then this over pi must be equal to this over pi. But there's another way we can do it. And we can ask, okay, well, what about just looking at the Goldbach equations, right? So let's just ask if Pj is a root, right? Can I use the Goldbach equations to construct that? So what we're going to be left with is negative, let's say T1 pi G primed of Pj. So this is our root approximation. And of course, this is equal to G of Pj mod pi squared. Right? And so we can look at this and say, all right, well, what do we have here? Well, this is equal to T1 pi Pj, and this is congruent to G pi mod pi squared, right? Via just this relationship here. These two are the same. And so now I can come along and I can just say, okay, negative T1 G prime of Pj is congruent to GPi over Pi mod Pi, right? Because my Pi squared is going to go away. But Pi is just congruent to 0. And so this is really negative T1 G prime Pj is congruent to G of 0 over Pi mod Pi, which is not congruent to 0 mod Pi. Therefore, is not congruent to 0 mod Pi. Right? So using these relationships here, a couple of ways, like I said, we could do it. We could just say that if this is congruent to this, then this over Pi has to be congruent to this over Pi, but we already know what that is, right? It's non-zero. But the other way we could do it is just to say, well, let's use the Hensel-Goldbach equations, but let's, instead of using the principal root, we already know that if alpha I, or if 2a is congruent to Pj, right, then we can come along and use this equivalence relationship here to swap out. And now what we have is the derivative is not equal to 0. And remember what we showed in that previous proposition, that if Pi is a divisor of some Qj and Qk, then the derivative has to be equal to 0. Showing that the derivative is not equal to 0 then tells us that there is no prime, that there is no prime in the prime set that divides both some Qj and some Qk. And so because of that, we have now proven that the GCD of each Qi and Qj is equal to 1. And so remember the 2a, the equation we have here is Qi plus Pi, and the product of all of these Q's is equal to the product of all these primes, some prime factorization, right? So we have just as many Q's as we have primes, but we also know that there's no prime that divides any two Q's, right? And so that means whatever Q is, so if Pi divides 2a, then 2a must be equal to Pi to the alpha I plus Pi, right? For all the primes that divide 2a. Now, what about the primes that do not divide 2a? Well, we know that those only divide one Q. And so that means that for any primes that don't divide 2a, then 2a has to be equal to some Pj alpha j plus Pk, such that k is not equal to j, right? Can't be equal to j because that would just be of this 4 here, right? And so all of the primes that divide 2a has to be of this form, right? So as an example, if we have 2, which is a divisor of 2, then 2a has to be of the form 2 to some power plus 2. And then each q is a perfect prime power in this case. And so this allows us to solve directly for 2a. So we know 2 divides 2a. So then 2 to the alpha 1 plus 2 must be equal to some perfect power, pj alpha j, and then 3 is the next prime. So now we're left with this. But this is a Catalan type equation. 2 to the alpha 1 minus some perfect power must be equal to 1. But remember, we had said earlier that Catalan's conjecture shows that 2 squared minus 3 equals 1 has to be the largest solution to this equation. Well, now we know what alpha 1 is. It's 2. So the largest solution to this is 2 squared plus 2, which is equal to 6. And notice that this forces 3. Well, 3 plus 3 clearly equal to 6. So the reason there are no counterexamples to the Goldbach conjecture is because the only counterexamples that could exist must be of this form. And because we just showed, luckily someone had proven the Catalan conjecture already, knowing the Catalan conjecture is true and knowing those solutions tells us the maximum value that 2a can be. And so that is my proof of the Goldbach conjecture. Hopefully there's no errors in it. I don't see any. But I really wanted to just give an idea of what it looks like. If there are errors, then we'll find them. But this is what doing real math is. And 6 years going back and forth in my spare time working on this has it's been enlightening. This same method can be used to show that every even number is the difference of 2 primes. And then once you have that, the twin prime conjecture and the polynomial conjecture follow directly from that. So as I said, there'll be a link to the paper online. And I'm curious to see comments or anything like that. But yeah, hopefully this has been an interesting experience for everyone to see what actual math looks like.